This lecture is about support vector machines. Support vector machines represent an effective machine learning technique and one of the most widely used and popular machine learning techniques used in industry and academic research. Support vector machines were introduced in early 1990s by Vladimir Vapnik and his co-workers. The basic idea in support vector machine is this. If we have a classification problem, we try to find a decision surface for that classification problem as a hyperplane in the feature space. For example, if we have a two-dimensional classification problem, the decision surface will be a line in this 2D space. If we have a 3D classification problem, the decision surface will be a 2D plane. In the case of an n-dimensional space, the decision surface will be a hyperplane with dimension n-1. What happens now if the problem is not linearly separable? So we cannot separate it with a line in the 2D space, with a plane in a 3D space, or with a hyperplane of dimension n-1 in an n-dimensional space. The solution is to convert that problem into a linearly separable problem by transforming the input space into a higher dimensional feature space where the problem is linearly separable. Let's suppose now we have a two-class classification problem. The positive class and negative class denoted here with blue and green. We can separate the two classes in this figure by several lines. So for example, with this line, or this line, or with this red line, which would be a better line to separate the two classes? Intuitively, it is the red line, because that line goes through the middle of the gap between the two classes. This is an example of a linearly separable problem in a two-dimensional space. In order to find the red line that best separates the two classes, we have to find what is called the widest margin. Here in this figure, we have two margins. This is one, and this is another one, which is the gap between the two classes. Intuitively, it's best to have a wider margin, and the separating hyperplane will go through the middle of that margin. In order to find the widest margin, or simply called margin, we have to find these examples here situated exactly on the margin, right, which are called support vectors. So the decision boundary, which you see here, is determined only by the support vectors. The other examples in the two classes do not matter too much. So if we find the support vectors, then we find the margin, and then the separating hyperplane, in our case the separating line in a 2D problem, goes through the middle of the margin. Let's summarize now the basic ideas used in support vector machines. If we have a two-class classification problem and the two classes can be linearly separated, we find the optimal hyperplane that maximizes the degree of separation between the two classes. So that we maximize the margin between the two classes. If we go back to our previous example, we have two classes which are far away from each other, and we find the maximum margin, as I explained before, and we find this hyperplane, which in our case is a line. But what happens if the two classes cannot be linearly separated? So let's say we have some green examples on this part of the hyperplane and some blue examples on this part of the hyperplane, but not that many. We can apply, we can use what is called soft support vector machine, and we find the hyperplane that maximizes the margin and also minimizes the number of misclassifications. So we allow some misclassifications if we don't have to many misclassifications. We'll talk about this approach later when in the soft support vector machine. But let's say what happens if we have too many misclassifications and we cannot use even this soft support vector machine approach. We map the data, which is not linearly separable, onto a higher dimensional space via what is called a kernel function, where the data can be classified with linear decision surfaces. We will have a discussion about kernel functions later in this lecture. Now let's see how support vector machine works. In a two-class classification problem, we denoted the two classes until now as being the positive class and the negative class, and in some cases as being class 1 or class 0. In the support vector machine formulation, we will denote the two classes as 1 and minus 1. Now let's remember a bit about linear regression. When we try to solve a problem with linear regression, we were looking for a model theta times x, if you remember, where theta was a vector of parameters and x was the input vector. And we are looking to find the vector parameter theta that minimizes the cost function, which was an error function. And if you remember, we had a special parameter which was called theta 0, and we called it intercept. And we included in the same form as the other parameters by multiplying theta 0 with 1. Now, in support vector machines, the parameters are called W and B is similar to what we called intercept in linear regression, and W is a vector parameter similar to the parameter vectors theta in linear regression. We can use the same trick, and we multiply B with 1, and then we will we can consider that we have only this part of the model. But remember, if you don't see B is always included in this vector W as being the first component of this vector W0. And then we have to identify a cost function in a similar way with what was done in linear regression. And we have to see what is the cost function in this case. So if you remember what we do in support vector machines, we are trying to find the widest margin that separates the two classes. So we are trying to find these two lines, and then the line in between these two margins will be the separating hyperplane. Now, this, if you look to this equation, this is the equation of a line in a two-dimensional space, right? So imagine that X has two components, because we have two dimensions here, input 1 and input 2. So X will have two components, X1, X2, and W will have two components, W1 and W2. All points on this line will satisfy this equation. In particular, there is a point here which we call support vector. That point there satisfies this equation. What about the points on the right side of this line? The points on the right side of this line will satisfy this inequation, Wx plus B greater than 1. The points on the left side of the line will satisfy an equation in the form Wx plus B less than 1. In a similar way, let's take this line. The points on this line will satisfy this equation. So in particular, we have two support vectors here in green, which will satisfy this equation. The point situated on the left side of this line will satisfy this inequation. So it will be less or equal than minus 1. Okay, now we want to try to find the two lines, the two margins, in such a way that we have the widest margin possible. So we have three lines. This is one line, wx plus b equal 1. Another line is wx plus b equal minus 1. And the line in the middle of these two lines is wx plus b equals 0, which will be our separating line or separating hyperplane in a higher dimensional space. Now let's take a line like this, wx plus b equal k, where k can be 1 or minus 1. In general, it can be proven that the distance between the origin and a line like this, for example 1 or minus 1, is this. So the distance between the origin and the line wx plus b equal 1 will be 1 over the norm of the vector w. And the distance between the origin and the line minus 1 will be minus 1 over the norm of vector w. Now, what is the norm of the vector w in our case? Usually we use a Euclidean norm. So we are here in a two-dimensional space, and as I explained before, x has two components, w will have to have two components, w1 and w2. And the norm of w2, the Euclidean norm, the norm of w, the Euclidean norm, will be square root of w1 square plus w2 square. I'm sure you are familiar with what an Euclidean norm looks like. So we can calculate the difference between this line and this line, which will be 2 over the norm of w. So in other words, this is the size of the margin. Now, to prove this, you have to do a little bit of maths. We won't do it in this lecture, right? But it's quite easy to do some maths to prove that the size of the margin is 2 over the norm of w. Now, our optimization problem will be this. We have to find the parameters of the model, w and b, such that for all the points in class 1, the blue class, wx plus b is greater or equal than 1. When it is 1. It's only for the support vectors is 1. Also, for all of the points in class minus 1, we have to satisfy this inequality. Wx plus b less or equal than minus 1. So we have to satisfy these two, but remember we have to find w and b in such a way to find the widest margin possible. So we have to maximize the size of the margin, which is this one. So this is the optimization problem which we solve in support vector machines. Now let's look at these two inequalities here, and let's try to do a bit of more work on them. So as I explained before, class 1 is denoted as 1 and is denoted as here, and class 2 is denoted with minus 1, right? And these are the two inequalities. How can we write them into just one inequality so that to simplify our problem? If we multiply this inequality with 1, nothing changes. If we multiply this inequality with minus 1, we change the sign of the inequality, right? So in other words, we can put these two inequalities together into one inequality like this, where we multiply on the left side here with y I, which can be either 1 or minus 1. So our optimization problem, you remember what we had? This was the optimization problem to solve, becomes this. Find the maximum of the margin. So in other words, find the parameter vector w which maximizes the margin, maximizes this value, so that to satisfy this inequality, right? But in optimization problem, we love to solve minimization problems, to find the minimum of an optimization problem rather than the maximum of a problem. And let's convert this maximization problem into a minimization problem. So we can say that rather than finding the maximum of this value, we can do the same thing by finding the minimum of the opposite, 1 over this value, right? And then we square W to get rid of the sign in case there may be some problems. So our optimization problem becomes like this: find the minimum of this value, right? So that this inequality is satisfied. And this will be the what is called the hard margin support vector machine formulation. Why is it called so hard margin SVM? Is because we do not allow misclassifications. We do not allow any examples to fall in between the margins. If the two classes are linearly separable, like in our previous example, there is only one unique global minimum value for this function, right? So the error function has a nice bowl-like shape function where there is only one minimum, one global minimum, and then there is a unique value W and B for which that function has a minimum value. So this is what happens in the case of when the two classes are linearly separable. But what if the data is not linearly separable, which is represented by most problems in real world? If the data is not linearly separable, we can allow some examples to fall within the margins, but we have to penalize them in order to make sure that we get a good model. This is called soft margin support vector machine, and we will discuss later. Another idea is to use what is called kernel functions. So let's say we have a two-class classification problem, and the two classes are represented here in blue and red. As you see, they are not linearly separable, as in our previous examples where the two classes were situated far apart from each other, and we could draw a nice line between the two classes. This is a much more difficult classification problem, as in order to separate the red examples from the blue examples, we have to draw a line like this, which would be very difficult, right? So we are here in a two-dimensional space. What can we do? We can use a kernel function, and for each data in this two-dimensional space, by applying that function, we transform it into a three-dimensional data point, right? So all of these points, red and blue dots in the two-dimensional space, will be transformed via a kernel function into a three-dimensional space, where possibly the two classes, red and blue class, can be separated by a hyperplane, which in this case is a normal plane, right? So if we take a kernel function and we use more dimensions, the problem may become linearly separable in a higher dimensional space, where we can apply the same support vector machines as explained before. So X will be transformed via a kernel function into this one, and the optimization problem will become this. So find the minimum for this value, right? So that this inequality is satisfied, where instead of X we have the kernel function here, right? So this would be the SVM problem formulation when you use kernel functions. But let's suppose now that even after applying after using some kernel functions, the problem is not a pure linearly separable problem. So for example, in this case, even when we apply a kernel function and we transform this two-dimensional problem into a three-dimensional problem, we cannot find a clear plane that completely separates all the blue examples from the red examples. So there are still misclassification errors. So in this case, we can apply what is called a soft margin support vector machines, where we allow some examples to fall within the margin or outside of this margin even. So this is what happens in the classical support vector machine. So we have we have the two margins here, right? The two classes, black points and empty points, right? And this is the optimal hyperplane which we found. As you see, some examples, there is one white point here on this side of the margin, but it's still, because this is the separating hyperplane, this will be still classified correctly as a white point, even if it's within the margin. The same with this black points here, because it's on the left side of the separating hyperplane, will be still classified correctly. But we won't like points to fall within the margins. But what about this black point here? As you see, this black point will be classified as white point because it's on the right side of the red line of the separating hyperplane. So this is an error, right? So we can say that we allow some misclassification errors, provided that they are not too many. And this is the formulation in the case of using kernels. And the SVM problem will become a little bit more complicated, and by adding some variables which are called slack variables. So what changes between this and the previous one? We add here a term in this cost function, and we will subtract some variables here which are called slack variables. Yeah? Okay, so this is the only difference. We subtracted a variable here, and then we added this term. Yeah, let's talk a little bit more on the next slide about that. So for each of the input patterns, we have what is called a slack variable, yeah, which holds for misclassified examples. So in other words, you remember in the classical hard support vector machine, we didn't have anything after 1. So all examples should satisfy this inequality to be greater or equal than 1. We allow them to be a little bit less than 1 for some examples, and each slack variable for each input examples will tell me how much I can allow for each input variable, yeah, for each input pattern. And the optimization function is changed. Rather than having only this part, we add another part here, which is the sum. We have here the sum of all these slack variables. So the sum of all these slack variables can be thought as of a measure of the total amount of misclassifications. So each epsilon I is for each for each input data point, right? And we add all of these misclassification errors, and this will tell me how much misclassification I can allow overall in this problem. And C controls the trade-off between between two conflicting goals. So in this new optimization problem, I have two goals. One is to maximize the margin, as in the hard support vector machine. So remember, we are looking to find that hyperplane that maximizes the size of the margin. Yeah, so this is the part that does that. And another optimization goal will be to minimize the number of misclassifications. So we have to minimize this sum here, right? But we have to satisfy two conflicting goals now, and C will control the trade-offs between these two contradictory goals. For example, if we are interested in finding the widest margin and we don't mind too much about the misclassification errors, then C will have a low value here. So in other words, we give importance to finding the widest margin possible. If, for example, we don't want to allow many misclassifications, so that means this term is very important. I'm not happy when with many misclassifications, C will have a big value. And in this way, when we find the parameters W, we'll try to find them in such a way to minimize the misclassifications. So this is the support vector machine formulation, the soft support vector machine formulation. The vast majority of the problems we encounter in real life are not linearly separable. So if we want to apply support vector machines in this case, we would have to use some kernel functions and transform the original data space into a higher dimensional space where the problem is linearly separable. But the feature space often becomes very high dimensional. And in machine learning, we hate working with too many dimensions. This is called the curse of dimensionality problem. So we usually want to reduce the number of dimensions to a reasonable number, because a classifier in a higher dimensional space has too many parameters and it is hard to properly identify that classifier. You've previously had a lecture on feature selection and feature extraction, where you were told exactly that. So if we have an original number of n features, in feature selection, you apply a feature selection method and you extract a few features and then use those features in training the classifier or the model. In feature extraction, rather than selecting a number of the original features, you calculate new features, for example, in the principal component analysis method. And you use those features in identifying the classifier. So it appears that in support vector machines, we are doing exactly the opposite. And this was quite revolutionary when support vector machines were introduced in early 1990s. So Vapnik argues that the fundamental problem is not the number of parameters to be estimated when we trying to identify a model. Rather, the problem is about the flexibility of a classifier. And the flexibility of a classifier is not characterized by the number of parameters, but by the flexibility, but in other words, the capacity of a classifier, which is formalized by what is called the VC dimension of a classifier. VC dimension is from the name of the two authors who introduced that concept, Vapnik, Chervonenkis dimension. The higher the VC dimension of the problem, the more flexible the classifier is and the better to learn is. But in practice, it's very difficult to identify the VC dimension of a problem, and we'll discuss a little bit later in the lecture, although I would ask you to read more papers about that, because it can be a quite theoretical topic. So in support vector machines, we solve a problem what is called structural risk minimization problem, that tries to find the classifier that minimizes two objectives in the same time. One is the sum of the training errors, is what we want in any classification problem, right? This is called empirical risk. But in the same time, we try to optimize a term that is a function of the flexibility of the classifier, which is called model complexity. The flexibility of the classifier being given by the VC dimension of that problem. So if we have a non-linearly separated problem, we will have to use a kernel function. But we have to use the kernel function, a good kernel function that such that in the higher dimensional space, the problem will become linearly separable. This is a very tricky part of using support vector machines, how to properly select the kernel function. This is equivalent to choosing the number of hidden nodes, for example, in a neural network. You will learn this next term about that. Or choosing the number of parameters for any other modeling technique. There are two types of kernels which are usually employed in support vector machine-based modeling. One is polynomial kernel functions, and another one is Gaussian or similarly are radial basis function kernels. And we start usually with a low degree polynomial kernel function. Yeah. And then we increase the degree of the polynomial if that doesn't work. Or we can start with a Gaussian kernel function with a reasonable width, and then change that width if it does not work well. Next term, you will learn about radial basis function neural networks, and you will know that SVM with radial basis function kernels are closely related to RBF neural networks. Now let's take some examples to understand how to use kernel functions. So let's say we want to try polynomial kernels first. And let's take this problem. As we see, we have to distinguish the x's from the circles, and the problem is clearly non-linearly separable. Yeah? So we have to learn this decision boundary here. So this is a two-dimensional problem, right? If we want to use the support vector machine, which only in the two-dimensional space, we won't be able to use, So we will have to use kernel functions. So how do we write the support vector machine problem? For us, if for class 1 we have this is the inequality that holds, and vice versa if y is -1, right? So as I said, because the problem is non-linearly separable, we cannot use the usual part like this, what we have in a two-dimensional support vector machine, where we have W1 and W2, and then W0 is the same with what we called before B, right? So usually if the problem would be linearly separable, we will use only this part here. What can we do if the problem is not linearly separable? So we can add more polynomial features. For example, we can square x1 and multiply with a parameter w4, or we can multiply x1 and x2 and multiply with a parameter w3, or square x2 and then multiply with w5. And now, in addition to w0, w1, w2 parameters, we have to identify these parameters, w3, w4, w5. So what kind of features like this we can use? Imagine that we have an infinite number of possibilities and higher orders can be used here. So this would be our problem when applying polynomial kernels. So let's say this is what we had by using those higher order polynomial features, and in the original space, yeah, the data was not linearly separable. But if we rewrite now and say that x1 is feature 1, x2 is feature 2, x1 times x2 is feature number 3, x1 square is feature number 4, x2 square is feature number 5, and we identify the parameters w0, w1 up to w5, and maybe other parameters, the data may become linearly separable in the higher dimensional space, where we can apply a standard hard support vector machine or soft support vector machines if there are some misclassifications in that space as well. Now let's talk a bit about Gaussian kernels with support vector machines. And this is how the idea works with support vector machines using Gaussian kernels. So let's suppose we have a classification problem in a two-dimensional space, x1, x2. So we have only two features, input features, and then the data is represented somehow in this two-dimensional space. And then we identify three important points in this space, or landmarks. We call them landmarks. Landmarks 1, landmarks 2, landmark 3, which cover the class well. In a way, is like a center of the class, or the most representative points which we believe are in the data, right? And we are going now to measure the distance between all the points in our problem and these three landmarks. So for any point x in our problem, we calculate how similar x is to the three landmarks, landmark 1, landmark 2, and landmark 3. And we use for that three functions. For example, f1 will be a function that gives me the similarity between x and landmark 1, and that is expressed as a Gaussian function. This is the expression of a Gaussian function, right, which actually you should be familiar by now, where L1 is the landmark number 1 and sigma is the spread of the Gaussian. So if one point is close to L1, so let's say if it just overlaps L1, then that function will have the maximum value 1. If it's far away from landmark 1, that f1 will be almost 0. In a similar way, we define similarity to landmark 2 and landmark 3 using these two Gaussians, yeah, were centered in landmark 2 and landmark 3. And the similarity measure is what we call the kernel. And in this case, we have Gaussian kernels, where Li is the center of the Gaussian, I and sigma is the spread or the width of the Gaussian. We can use other Gaussian, other similar functions, like, for example, radial basis function kernels. And remember that in our original space, we had only two features, x1 and x2. And now by using these three Gaussians, we transform the data from the original two-dimensional space into a three-dimensional space where we, instead of x1 and x2, we have f1, f2, and f3, the three similarity measures to these three Gaussians, right? And then let's give an example. For example, if for a data point, for example, feature 1 is 1, feature 2 is 0, feature 3 is 0, and then we have these parameters of the model, we can calculate the product between the parameter vector and the feature vector, make all the calculations, which will result in 0.5, which is greater than 0. So in this feature space, support vector machine will predict that this point is in class 1. That's it about kernels. I think I guess you have some rough ideas on how to use kernels. Let's move to another issue now, which is Vapnik-Chervonenkis dimension. I just quickly told you about that, that this expresses how flexible a classifier is. However, this is a quite theoretical topic, and in order to calculate the Vapnik-Chervonenkis dimension for support vector machines, we will have to refer first to a finite hypothesis space and then to an infinite hypothesis space. It's a quite theoretical issue, and then I wouldn't like to take much of your time because it's more important to understand how the basic support vector machine works, how you use kernels properly, what is a kernel, and how to apply support vector machines for a real world problem. But anyhow, if someone is interested, I would refer them to some titles in the reading list, and I wish you much success in digging into this topic. What you have to keep in mind is that the VC dimension for a problem will give you the number of required training samples to be able to train a support vector model with a certain desired error. But in practice, it's very difficult to calculate. And to be honest, I'm not sure how many of you will deal with this issue unless, for example, you are interested in very theoretical machine learning issues in a future PhD or later in a future academic career. But for applying support vector machine for a real world problem, I think that's enough to know what the VC dimension is and what is the purpose of it. So, as I said at the beginning of the lecture, support vector machines represent one of the most popular and effective machine learning methods used by many practitioners and academic researchers. Why that? Because the training is relatively easy, right? And it's because there are no local optima. As I told you, the optimization problem has only one minimum, and there is only one solution. And it's easy to find that minimum, but that happens only if the problem is linearly separable, which doesn't happen in practice most of the time, right? But then we use the kernel trick, and we take the non-linearly separable problem, we convert into a higher dimensional space where the problem becomes linearly separable, and we use the SVM to linearly classify the two classes, right? Or we can apply what is called a soft support vector machine. But it's a good method compared, for example, to other neural network, to other methods like neural networks, which will have a problem with local optima. It scales relatively well to high dimensional data. So this is another advantage of support vector machine. And the trade-off between the classifier complexity and the error of the model can be controlled explicitly. However, the most tricky part in training support vector machines is how to choose a good kernel function. As I said, if you choose a good kernel function, data will be linearly separable in a higher dimensional space. If not, it will not be linearly separable, and you will still have the same problem as with other modeling techniques. So today we discussed about the support vector machine problem formulation, what is a hard and a soft support vector machine, and how to use kernels, and just review and define the VC dimension.